On this adventure, we're going to introduce internal direct products and look at several examples. So in this optional video, we're going to talk about where the notion of direct products comes from. So the problem is you're given a group, and you want to determine whether or not it's actually isomorphic to a direct product of two other groups. Why would you want to do such a thing? Well, because then you're replacing what's possibly a large group with this product of smaller groups. For instance, if G has order 100, and each of these is H is order 20 and K is order 5, well, now you have two smaller groups. Well, one way to get a handle on this is to study direct products again and study how these two groups are related to the direct product. And one way to see that is to recognize that there's an isomorphic copy of H that's a subgroup in the direct product. This isomorphic copy consists of ordered pairs where the second coordinate is the identity. Similarly, there ends up being an isomorphic copy of K that's a subgroup in the direct product. These are those elements where the first coordinate is the identity. In other words, this is sort of the generalization of the coordinate axes in R squared. The coordinate axes are given by setting one of the coordinates equal to 0. These coordinate subgroups, so to speak, are given by setting one of the coordinates equal to the identity. And each of the coordinate subgroups is isomorphic to one of the factors in the direct product. Why does this matter? Well, there's some nice properties you can see about these coordinate subgroups. Namely, for any element in the direct product, you can certainly rewrite it as a product as follows: H times E times K. In other words, it factors as an element in H prime times an element in K prime. This is familiar with the fact from linear algebra that, or actually from high school algebra, that you're going to be able to write everything as a x-coordinate and a y-coordinate, which is generalized to linear algebra to saying that everything is going to be able to have a unique representation in terms of the two basis vectors. It's a similar idea, only now things are non-commutative and we're talking about multiplication instead of addition. So that's one thing you can observe. Another thing we observe is that we actually have commutativity here. So now if you actually forget that these were ordered pairs and call this H prime and K prime, we're saying that elements in H prime commute with elements in K prime up to multiplication. The third observation one can see is that the only elements these two coordinate subgroups have in common is the origin, or the identity coordinate, ordered pair. So we see, given a direct product, the factors correspond to certain isomorphic subgroups, which I'm calling coordinate subgroups for now, and these coordinate subgroups have these identifiable properties. What it turns out is that these identifiable properties classify direct products in the sense that if you can find two subgroups in G, H prime and K prime, that satisfy these three properties, then G is actually isomorphic to that direct product of those two subgroups. So in other words, they do in fact form coordinate subgroups. So a generalization of linear algebra in some sense. Those subgroups sort of form a generalization of a basis. But only in a very weak sense that you've got this decomposition. Nothing about uniqueness. But it's a start. So in the other videos on internal direct products, we will define the internal direct product, and you'll see it involves these three conditions. And this is where these three conditions come from.